Ooh. Don't want to say it. Yeah, I kind of. Yeah. Yeah. Oh, you have blue. He's gray. Okay, so if you look at the lab, okay, she's also a
Okay, welcome back. It seems like it's been a long time since we were together. Hopefully you all watched that video that I posted on Wednesday at home. It took a long time to process, so it was a little later in the day till I got it up than what I meant it to be. I also talked a little bit longer than what I meant to. I just kind of kept going, and so I apologize for that. It was a little bit longer, the two videos together, than what I meant to, but then we won't be as rushed later on, I guess. So a little business, the drop day is approaching. So that's always the Friday of spring break, March 10th. I did post on Blackboard a decision tree if you're trying to decide whether it's appropriate for you to drop or not. Take a look at that. It's under the syllabus, the tab. I think it just says syllabus. That's where I stuck it, just because it seemed like there wasn't a lot of other stuff there. So take a look at that. Basically, if you drop the course, it shows up with a W on your transcript. So yeah, if that's something that you're considering, you're welcome to talk to me about it. And I don't know if I can give you any insight, but if you do decide to drop lecture, keep in mind that they will automatically drop you from lab. If you're doing fine in lab, though, we want you to stay in lab and not have to retake that as well. So just talk to your lab professor. She needs to get a course override. It's just a matter of sending an email. But try not to do this, at 4:30 on the Friday of spring break. It's good to think about it now. Okay, now we do a lab exam this week, and that might play into your decision, but just a heads up. Basically, after that withdrawal date, it's very difficult to withdraw. You would have to get a late withdrawal. Typically, you need something to happen to you after that withdrawal date that makes it appropriate, like you had some crisis after the withdrawal date, not just, it's a week before the end of class and I'm not doing good. That's not a good reason to withdraw. So be thinking about that if that applies to you. I realize that our next exam, a couple of you have mentioned to me that's the day of your nursing interview. So I don't know how I would have seen that coming, but I didn't realize that. I will, as we get closer, if you have, again, a nursing interview on March 20th, you may decide you want to take the exam on Friday. That's fine with me. You may decide you want to take it at a different time, either on Tuesday or Wednesday, ideally Wednesday morning. So I'll be flexible with that. Be in touch with me and we'll schedule a different time. If it's Monday afternoon or whatever, if you can't get here, that's fine. So also the exam last Monday, I did post your scores. I did end up rounding up about 2%. So what's posted is a slight curve. The mean was a 72, so a little lower than the first exam. There were 5 people that only missed 1. And at first I thought, oh no, I made a mistake, but they didn't all miss the same one. It was lots of different things. So I had actually 5 people that once I rounded up, ended up with 100. So come see me if you want to talk about that sometime. Usually the third exam, people do a little better on. It's just a little bit less abstract, the information that we're getting into now. But yeah, think about, you know, if you need to change your studying habits, think about what you can do different. All right, any other questions before we keep going? Questions, comments? Okay, don't be afraid to stop me and ask about anything. I think this is where we left off. So we finished viruses. Probably the most difficult parts of the viruses is just the replication. So 2 different replication cycles. I don't think it's, anyway, that's probably, you know, other than kind of just the facts that I fed you about viruses. But it's important to kind of understand a little bit what a virus is and, you know, the parts of it, the capsid, you know, nucleic acid and stuff, when we move into immunology and thinking about how our immune system can detect that viruses are present within our cells. And any specific examples, remember, we're going to talk about some later in the semester, so don't, you know, if I talked about Ebola or whatever, it's just an example. So thinking about how to kill microbes when it's appropriate to do so, we started talking about heat primarily and the use of moist heat. Some different applications like pasteurization is using moist heat typically. An autoclave in this example of using heat under pressure. Usually we try to use moist heat because we don't have to bring, water is just a little bit more penetrating than using dry heat, it doesn't take as long. But sometimes if you have something that you're trying to cut down microbial numbers on and it will damage it to get it wet, it might be appropriate to use heat and not use moisture. So you could use a hot air oven to usually to sterilize something. It takes a little bit longer, requires a little higher temperature, but not super high. 170 degrees Celsius, that is about 340 degrees Fahrenheit. So, you know, that's kind of a cooler oven, like that you would bake cookies in, you know, it's not super hot, but it takes some time. It would take a couple hours. And of course, some things, you know, might be at risk of possibly catching on fire, like some kinds of paper or things that you might not want to use dry heat. Another application we use all the time in the lab is incineration. So whenever you're flaming your loop, basically you're burning off any microbes that might be on that wire, and make sure that you are getting that wire red hot. Just waving it through the flame might not be good enough. So take the time to do that. Oftentimes, you know, medical waste, we would just incinerate, and that does a good job of sterilizing anything there. Here's another picture of somebody flaming their loop. This picture on the right, that's called a bacterio incinerator. Did I say that? Bacteria incinerator. Basically, you can just stick your loop inside of there and it will like flame it like really quickly, and then you don't have to have an open flame in the lab. So if you are, you know, inoculating a lot of plates, our lab workers that do that, they use one of these inside of the fume hood, and then again, they don't have an enclosed space. They don't have to worry about an open flame, and it's kind of quick and efficient. So using high temperature is going to kill microbes. Is the opposite true using low temperature? No, it doesn't work the same way. Refrigeration and freezing, assuming that we're trying to kill bacteria, would be considered bacteriostatic. Remember that suffix static means to basically keep a cell from growing. If it was cytal, it would be killing a bacteria cell. So for instance, refrigeration, that's about 4 degrees Celsius, is just going to slow bacterial growth. So in the lab, when you inoculate your plates, we put them in the incubator overnight, and then we keep them in the refrigerator until you come back in lab, just to kind of keep everything viable. If we let it grow for a week or so, then it might overgrow and kind of dry out and die. So again, most organisms are not going to be able to grow at low temperatures like that. There are exceptions. We said psychrophiles are going to grow optimally at lower temperature. They still grow kind of slow, to be honest. And there's all sorts of different shades to that. Something like this organism, Listeria monocytogenes, every once in a while you hear about foodborne outbreaks with that organism. It's an organism that actually grows really well in the refrigerator. So, you know, if you got a little contamination in the meat processing plant, lunch meat is a common thing that's contaminated. And then those numbers of bacteria will continue to grow in the refrigerator much quicker than maybe some other organisms. It doesn't grow optimally in the refrigerator, so it's not a true psychrophile, but sometimes we call it a facultative psychrophile because it still grows pretty well, even though it's not optimal. And of course, even freezing doesn't kill cells. It might damage some of them with ice crystals or whatever, but if we want to keep cells for a long period of time and just store them, like we see here in this Eppendorf tube, we'll often store them at minus 80 degrees Celsius. So that's minus 112 degrees Fahrenheit. So that's really cold. When we thaw that cell sample out, usually there's enough of them viable to, you know, that they take off and grow just fine. Other methods of controlling microbial growth, we're kind of thinking about physical methods here. In general, just depriving microbes of water is a good way to kill them. So desiccation, that's just a good way. When do we use that? When we are trying to preserve food. So in that picture, what that shows is people drying apricots in the sun. If you've ever bought an apricot in the store, they go bad really quickly. A real apricot, but you dehydrate them, and then bacteria need water for their metabolism, and so they don't rot nearly as quickly. Another method of desiccation really is called lyophilization, and you could just think about, that's a fancy way to say freeze drying. So how do we freeze dry something? Typically, you would expose it to liquid nitrogen that freeze it really quickly, and then you expose it to a vacuum, which kind of sucks the ice crystals off of it. So essentially, you've got sublimation, where you're going from the solid water's going from the solid stage right to the gaseous stage, missing that liquid stage. So that causes less damage to whatever you're trying to dehydrate. When might we use this? We could store cells this way. Also, it's a good way to store food. So astronaut ice cream, that's basically been freeze dried or lyophilized. Typically, you would add some water to that to make it taste a little bit better. Backpacking food, it's a nice way to, you know, carry some food that's real lightweight, and then you just add water to it when you eat it. And osmotic pressure, really essentially that's the same thing. You're drying something out. Typically here we're thinking about preserving food. You might add large amounts of some solute like salt or sugar, not just to make it taste good, but to create a really nice hypertonic environment. So again, water leaves the cells. And by cells, I mean the cells of microbes that would be rotting the food. So, you know, if you're trying to preserve strawberries, for example, we don't really care so much about removing the water from the strawberry. It's removing the water from the microbes that would, you know, cause that would proliferate in the strawberries there. Okay. And this actually does a little bit better job of inhibiting bacteria. Fungi are a little bit more resistant to being in a hypertonic medium, so it's often fungi, molds, that are spoiling our food in the refrigerator, for example. Okay, and then just a physical barrier, air filtration. This really, I see a lot of ads for this during the pandemic, you know, advertising at home, filter your air, keep it clean. I don't know really how well those kept anybody from getting COVID. But certainly one application is using these HEPA filters in a fume hood. So in a place where, you know, like our fume hoods up in the lab, when we're streaking out lots of stock plates for the lab, we want to kind of go that extra step of aseptic technique. And we have our air filtered just to try to keep our cultures pure. And essentially, you know, that's what the face masks are that we've been wearing around for a couple of years. Even something with a cloth with really big spaces in it. Certainly viruses can fit through those masks that we wear, but oftentimes the viruses are hitching a ride on you know, saliva and things that what we cough out. So it's going to do a good job catching that. So. And here's an example of using another kind of filtration if we're trying to disinfect or sterilize, usually even sterilize a liquid. We would pour the liquid in here. Usually we have to attach some kind of a vacuum to force the liquid through the membrane filter. And again, the pores can be small enough so that even viruses can't fit through there. So we essentially, this is a good way to sterilize you know, anything, especially that we can't heat, things like antibiotics or vaccines, any kind of drug. Here you can fix a filter up even to a syringe if you need a really small amount of something. Back in 2012, there was a really interesting, sad case study. You guys were pretty young in 2012, but there was a New England compounding pharmacy that made it prednisone basically, and it wasn't doing careful enough quality control. And it turned out that their prednisone was contaminated with a fungus. And people that got prednisone shots, especially in their kind of spinal column, if they were having some back pain, developed fungal meningitis. So very serious infection. There was 64 people died and over 800 people were sickened. Okay, and that pharmacy has long since been shut down. So, you know, when something needs to be sterile, there are ways that we can do that. And again, we have to check and make sure that those ways are working. All right, so the last physical method that we'll talk about is radiation. Again, really heat and radiation are probably the big two things that are used pretty widespread. And we talked about using radiation several times before. So two kinds of radiation, ionizing radiation and non-ionizing. So let's start with ionizing radiation. Okay, so and of course this is our X-rays and our gamma rays. So as the wavelength, you know, gets shorter and shorter, there's more energy to those rays, and they're going to cause more damage in the cell. So ionizing radiation, this creates ions. So an ion is a charged particle, right? So it's going to pull electrons off other molecules. So that's going to just cause all kinds of damage in the cell. We talked about how before that ionizing radiation can break one or both strands of DNA. And it does that by oxidizing those covalent bonds. So those phosphodiester bonds between the phosphates and the deoxyribose sugar, those are covalent bonds. We talked about how those are the strongest ones in nature because they're sharing the electrons. But covalent bonds are actually widespread in cells. They're in proteins as well as DNA and things like you know, water and carbon dioxide. hydroxyl radicals can also be created. That's a reactive oxygen species. It's gonna, again, be pulling electrons off of other molecules. So in terms of trying to use this to cause this damage, that's our goal. We're thinking about using radiation to kill bacteria and other kinds of microbes. It's kind of nice because it doesn't cause any heat. So you can use this method if you're trying to sterilize something that's heat sensitive. And you don't have to have a very long exposure. It's pretty rapid. Depending on what kind of radiation you use, it can penetrate even through solids. So has some potential to be used. So the kinds of ionizing radiation are gamma rays and X-rays. And I'll just say right off that we don't really use X-rays as a disinfectant, even though they penetrate really well through solids. You have to have such a long exposure that it's just not very practical. Okay, so we don't really use X-rays very much for this purpose. Primarily, if we're going to use ionizing radiation, we're going to use gamma rays. Where do gamma rays come from? Well, they come from radioactive elements. They're emitted from radioactive elements, something like cobalt 60, I think. So right there is part of the problem in using gamma rays, and as far as having them be accepted by the public to be used, because if it comes from a radioactive element, a lot of people think, well, it's going to make whatever you're trying to sterilize radioactive. And that's not the case. Many studies have shown that that's not the case, but still people that don't understand that or don't, are not willing to accept this very easily. But it's growing more and more acceptance. Anything that has been irradiated, commonly we use gamma rays for medical supplies and food. Anything that has been irradiated is supposed to have this sign on it on the packaging called a radura, radura, radura. So if you look at the potential here, I mean, here's two groups of strawberries that were irradiated. And the one, the one on the right was radiated, and then you wait a week, and the one on the left that hadn't been hit with the gamma rays, it's all rotten. So there's a lot of potential here to really drastically cut down on wasting food. I can't imagine how much produce is thrown out in grocery stores every week just because it goes bad. Again, it has been kind of slow to be accepted. Partly again because of the whole radioactive thing, which is not true, but it just changes the flavor slightly of some foods. So again, that works better for some foods than others, and it does reduce the certain vitamin content slightly for some foods as well. So there are some negatives, but again, it has a lot of potential. I kind of changed some content here. When I say penetrate better, I don't really explain that. Let's change this to it penetrates well. But it does take some time. It's not just bam, you hit it and it's sterile. You have to leave some exposure time there. But we'll say but takes some time. And that reads a little bit better. Okay. Let's see. Yeah, so a lot of medical supplies like bandages, lots of foods, and there's a list of foods that have been okayed by the FDA to be irradiated, especially fresh fruits and vegetables. That spinach. We had a big spinach outbreak. I think it was E. coli that was contaminated spinach, and it's really hard. You can't heat the spinach if you want to sell fresh spinach. So this is one way. And as we have these foodborne outbreaks, then more foods tend to be okayed to be, hit this way. All right, so the other kind of radiation, non-ionizing radiation, or UV light. If you're in lab, you just had a lab about this last week. What kind of mutation does UV light cause? Yes, thymine dimers. Good. Lab exam coming up. Okay, so two thymines on the same strand will bond to each other covalently. And then if the cell doesn't have, there's different, we talked about the different repair mechanisms, both light mechanisms and dark mechanisms. If they can't keep up, if you have a long enough exposure, then that's going to cause a lot of mutations in the cell. Non-ionizing radiation, like UV light, doesn't penetrate nearly as well as the ionizing. So it does penetrate really well through air, somewhat through liquids, not at all through solids. So still some applications. Here's one example. We're using UV light more and more in water treatment plants. And you can see that the flow has to be kind of regulated, but it looks like those light bulbs are right down in there in the water. You gotta regulate the flow rate so it has enough time, but I've read that it does a little bit better of cutting down on just all sorts of microbe numbers, a little bit better than dumping a bunch of chemicals in the water. So thinking sewage treatment here. You do have to be aware that, just like, you wouldn't want to be exposed to gamma ray, you wouldn't want to be exposed to ultraviolet light as well. Especially, so, give us a sunburn if we're exposed to it too long. Our eyes are especially going to be sensitive to UV. So you have to use it in a way that it's not going to be shining on humans, obviously. But again, lots of applications, treating water, all those, those splash pads that are kind of popular now, or could spray each other. That water gets circulated underground and is supposed to be hit with UV bulbs like this. Just treating it with chlorine is not as good because that cryptosporidium protozoa, if you watch the lecture that I posted on Wednesday, is somewhat resistant to chlorine. So we think that UV does a better job of that. And if you have maybe all shared chemical goggles in chemistry class, those might, get hit with some UV light just to kind of disinfect them in between classes. Some of you may have a little, I've seen on the market the toothbrushes that have a little UV lamp. Personally, I don't feel like I need that level of disinfection. Like I'm only using my toothbrush. I don't feel like it needs to be that clean, but we all have a line that we draw. There is a UV lamp on fume hoods. Again, when it really has to, when you have to really be careful, that's a good place to, again, not while you're working, but just kind of cut down on any growth that might be in there. And I wanted to point out this figure from your lab book, from your textbook, OpenStax. It talks about, what thymine dimers are, and it calls, okay, so these are hydrogen bonds, right? But this bond, it looks like it's calling this a hydrogen bond, and that's not accurate. That's supposed to be a covalent bond that's part of thymine dimers. So it's a detail, but I don't like it when something's printed incorrectly. One more application. I showed my lab this morning, but say you have a patient in a hospital room that had some, superbug, some antibiotic resistance infection maybe, or C. diff, another infection that's kind of hard to get rid of. This is another tool. Maybe you wheel in a UV lamp into the hospital room, you leave the room, you turn it on remotely, leave it sit there for 15 minutes, surface disinfection, whether it's disinfection or sterilization, maybe it depends how long you leave it there, turn it off remotely, come in, move it to a different spot in the room. Just another tool besides some of the chemicals that we'll talk about next to try to get rid of anything that we don't want growing. All right, questions. Okay, don't be afraid to throw something out. If you wonder about something, I may not know, but I can always look it up. Every once in a while, this brings out, you know, somebody thinks of something. Okay, so there's some chemicals that I would like to talk about as well. Before the pandemic, we were, I would say, even kind of obsessed with using antimicrobials even before the pandemic. It's all about risk assessment, right? Like, how clean do we need surfaces to be? There's been had been a little backlash against that, again, prior to the pandemic, that, you know, maybe we don't need to be using all these chemicals everywhere. You know, if you get a manufacturer of a certain chemical and then they start lobbying Congress that their chemical needs to be in everything, and then it kind of gets a little bit out of hand. We're starting to see how some of these chemicals are, you know, build up in our tissues, that we're peeing them out. And, you know, maybe that's not appropriate. Maybe we need to save certain chemicals for certain situations. And, you know, in the home, we probably don't need the same level of clean that what we would need in hospitals, for example. So, you know, there's always choices to make, you know, whether to use a certain chemical or, you know, which one do you use? There's a lot of different cleaners out there. How do you decide which one to use? Any thoughts? Trying to decide between Pine-Sol and Lysol or what? What do you think? You should probably figure out what you're trying to do. Good. All right. So let's write that down. Ideally, a good chemical is going to be broad spectrum. Okay. So in other words, kills all kinds of microbes. Okay. Now, maybe if you're taking a drug, you might not necessarily want that. And we'll talk about that more as we get into our antiseptics. But usually, if you're trying to get a surface clean, you don't say, I want to kill bacteria, but not viruses, or, you know, you just want to get it clean. Okay, so good. Anything else that you can think of? Yeah. Right. So you have to think about the surface. You have to think about whether it's going to leave some residue, if it's going to stain it. Good. So a good antimicrobial, well, let's say, would leave no residue. Okay. Do you really want to use iodine to clean your kitchen counter? Probably not. Yeah, that might not be the look that you're going for. Okay. You're not. This is the one that I thought you would think of first. Nobody's saying. Yeah. So ideally, going to have a short exposure time. Okay, let's write that. Yeah. Good, right? That's a good one too. So let's see, how can I say that? We'll say low side effects to humans. Okay. So what about if it's soluble in water and useful at low concentrations? That means what? It's going to be inexpensive. Okay. Ideally, yeah. Ideally, it's going to be cheap. And I thought, it should smell good too, but that's kind of a luxury, probably. All right. So good. So as we think through our different chemicals, we'll keep those things in mind. So we've got 5 different chemicals. There are more. I've just kind of pared the list down to kind of be the ones that maybe are most common. and I've split them up into kind of low, medium, and high level disinfectants or antiseptics. A low level disinfectant or antiseptic, like our soaps and detergents, they're going to be useful. Remember, we had that chart of microbes, the ones that are easy to kill, the ones that are hard to kill. A low level disinfectant would be useful against the ones that are easy to kill. And then medium level would kind of work off that chart, and high level disinfectant would be able to kill endospores. Okay, so we'll start with a couple of low level ones. Soaps and detergents are examples of surfactants. And there are other chemicals that are surfactants as well, but soaps and detergents, we'll start there. So basically, a surfactant is going to reduce the surface tension of liquids. And then when it decreases that attraction between molecules, then they're going to basically be released and wash them off. So what's the difference between a soap and a detergent? There's basically, a soap is going to be produced from natural products. And a detergent is going to be synthetic. So it's really just how we make them, whether we consider it a soap or detergent. Both of them are going to be good degerming agents. So that was a term that I defined last time. Again, both soaps and detergents. That just means it's like a physical scrubbing. Okay, so when we use soap to scrub our hands, that's going to just kind of a physical removal of dirt and any microbes that are stuck to the dirt, and then we rinse it away. So an example of a detergent that's commonly used, quaternary ammonia, or sometimes we would just call them quats. They work by inserting into membranes. So we'll take a look at a couple structures in a minute. Right into that phospholipid bilayer to disrupt the integrity of membranes. They have a lot of good qualities. They are cheap. They're colorless, so they're not going to stain anything. They're very stable, meaning they're not going to dissociate and become ineffective. And they're non-toxic. Okay, also going to be broad spectrum. So work on a lot of different microbes, bacteria, protozoa, viruses, and fungi. Okay, so they check a lot of boxes. Here's just, not to memorize structure, but soaps and detergents are going to have this hydrophilic head, and it's this hydrophobic tail that's going to insert into membranes. Here's the OpenStax book here. Here's a couple of, again, don't memorize these names, but these are quats. These are quaternary ammonias, and you can see they're pictured with the little blue head here. So here's like the head of the molecule, and then it inserts into the membranes. And when the membrane's not intact of a cell, then stuff's coming in that's not supposed to come in, stuff's leaving that's not supposed to leave. It's not going to be able to maintain that proton gradients, and not going to be able to metabolize ATP to produce ATP in respiration. Okay, so this is harming bacterial cells much more than our cells. And that just occurred to me before we came into class. Okay, why are soaps not bad for us too? As long as you're not, going to town too hard, not washing your hands, too often. The outer layer of our skin is dead. Okay, so that's kind of a protective barrier for soaps. And so always have to think about, that? How is it, harming bacteria and not us? Still considered kind of on the low end, or maybe getting up a little bit higher on the scale of an intermediate level antimicrobial. There's lots of different applications for using phenol. Phenol, this is phenol right here, also known as carbolic acid. If you remember, I think maybe the last we mentioned him was the first day of class, but Lister was the name of a guy, 1850s, 60s maybe, that advocating spraying carbolic acid in the operating room in order to cut down on infection. And that did a great job. We now know that phenol is pretty toxic to us too. So doctors that worked in those conditions had terrible respiratory problems. Their fingernails came out, their hair got bleached. So we don't do that anymore. We don't spray phenol in the operating room. We don't even use it as on the skin. We've got lots of other options that are not that toxic. Again, that was Lister. And for many years, that was sort of the gold standard of disinfectants. That's kind of what you used, because we didn't have a lot of other choices. Today, we have manipulated that phenol molecule a lot. Anything that's phenolic means that there's more than one phenols basically bonded together. Like this is a bisphenol, 2 phenols. And I'm not gonna worry about writing the names of the molecules on there because it's just an example, but this is called O-phenol-phenol. And for many years, that was the active ingredient in Lysol. I mean, when I was a kid, that was, if somebody was sick at home, you sprayed Lysol around everywhere. Now the active ingredient in Lysol is not O-phenol-phenol anymore. It depends what kind of Lysol you're using. I think it's an alcohol actually that's in it now, most often. And this other molecule here is hexachlorophene. That's the active ingredient in I guess you call it an antiseptic called Bisohex, which I'm not sure if that's still used in hospitals. Sometimes surgeons wash their hands in it. They used to bathe newborn babies in this until they realized that it had the potential to cause some neurological problems. So we pulled, again, most phenol applications we pulled way back from, and we try to use other things. It still is the active ingredients in that, what's it called, chloroseptate. If you ever had a sore throat, that cherry spray, that phenol has kind of a numbing effect in your throat. But again, kind of the list of things that we use any phenol or phenolics for is not as long as what it used to be. That triclosan, I don't know if you've heard of that, but that was a phenolic that used to be in everything, like, cutting boards and high chair trays and trash bags and everything. And so we started to understand that perhaps this chemical was doing more harm than it's good, that we don't really need to add antibacterial chemicals into everything that we're in contact with. Okay, so that was outlawed maybe 6-7 years ago. So moving up to the halogens, lots of examples of halogens. Of course, if you picture the periodic table in your mind, the halogens are near the right side. They're the group of non-metal elements that are quite reactive because their outer shell of electrons is not quite full. So they're trying to pull electrons from other molecules to fill up their outer shell of electrons. So some examples: chlorine, iodine, bromine, fluorine. We're going to concentrate on the chlorine and the iodine, talk a little bit further about those. Bromine doesn't probably have as many uses. I hear about people putting it like in their swimming pools or hot tubs. It's a little bit less irritating than chlorine, also a little more expensive. Fluorine, of course, we add it to our water, and that helps build up our tooth enamel and cuts down on tooth decay. So again, mode of action, pulling electrons from other molecules. So it's oxidizing other cellular components. And in terms of what that harms in cells, especially is going to be harming to proteins because it disrupts the bonding in proteins and enzymes and denatures them. We still consider them intermediate level. Things like bleach and iodine, it's true with a long exposure time, they will also kill spores, but I think it has to kill within 10 minutes to be considered sporicidal. So it takes a couple hours to kill endospores. So again, considered that intermediate level. All right, so if we look at some applications of chlorine, I know like that's kind of the first thing that I think of if I want to make sure some surface is really clean at home. I would get the bleach out. It's considered a pretty strong disinfectant, and it's one of the quickest acting ones. So all disinfectants need a little bit of contact time, but again, chlorine, you pretty much think on spraying it on, and it kills pretty quickly. It does have the disadvantage of being susceptible to an organic load. So I talked about that in the beginning of the lecture that I recorded there of this material, that an organic load, that just refers to something that is very dirty, or something like a vomit or diarrhea or blood. That's an organic load. So again, if you have some, say, vomit to clean up, you don't just hit it with bleach and wipe it up. If you're trying to clean the floor, you gotta get that organic material off, and then you gotta hit it with chlorine again. I mean, you may want to hit it twice. That's totally, I probably would do that. Another disadvantage is it's sensitive to light and pH. So when we buy bleach, you always buy it in these opaque containers, and that's having to slow down the disassociation of that bleach. When it dissociates, then it's not effective anymore. So again, the light will make it dissociate. And again, if you're adding chlorine to a swimming pool, you got to check the pH, because when the pH gets high enough, again, the chlorine will dissociate, and then no matter how much you pour in, it's not going to do any good. So you might be tempted, say you need some bleach for whatever, to whiten your whites or whatever, you might be tempted to get a big bottle of it and then say, oh, this will last me for years. Well, even when it's in an opaque bottle like that, it will start to dissociate between like 6 and 9 months, and then it won't work as well. So it's a good bet to just buy your bleach in little containers and use it up, and then get more. Because again, if it's not making your white, then it's not going to be killing the microbes the level that you want to as well. So we see chlorine, that element, in many different forms. Sometimes chloramine is actually ammonia with the chlorine atom added to it right there. Now, so that's a liquid, actually, chloramine. You never want to mix bleach and ammonia. In fact, it's kind of hard to find ammonia at the grocery store anymore, because if you mix both of those liquids, the fumes that result are toxic, like they can kill you. So you would never want to mix those two things. But again, if they're a liquid, then it's okay. It's the gas fumes that are bad. The advantage of chloramine is that the killing power lasts a little bit longer. So if you put it on a surface, it's going to stay clean for a little bit longer and not just get contaminated right away. Elemental chlorine hypochlorites, that's a fancy way of saying bleach. Okay. So all of those have a lot of applications in water treatment. So again, swimming pools, sewage treatment, drinking water treatment, the sewage treatment plants that add some kind of chlorine at the end. You see this big kind of pools. Well, they add the chlorine, and then they have to let the chlorine kind of kind of evaporate off before they can release the water back into, say, the Grand River or whatever. Chlorine dioxide, you can use it as a gas if you got maybe some big room that you want to disinfect, a bigger space. There is some resistance. And the one that the instance that I mentioned again on the recorded lecture was the cryptosporidium. I know when we say crypto today, it has a different meaning, but this is that protozoa that forms those cysts. I talked about that 1993, I think, instance where they had some kind of massive failure at the Milwaukee water treatment plant where 400,000 people got sick, diarrhea from cryptosporidium. So it wasn't that they weren't treating their water. There was some kind of, they didn't quite figure it out. They replaced a bunch of filters apparently, and the problem diminished. But that protozoa is a little bit resistant to chlorine. So that's what they found, that the UV light actually does a better job of killing that organism than just using some kind of chlorine. And then iodine. A lot of antiseptic uses for iodine. Okay, so remember, antiseptic, that means it's used on some living surface, I mean, probably humans, but some animal or human surface. So a lot of wound treatment, or before a surgery treatment, are common for iodine. It penetrates through some kind of organic substance, again like blood or whatever, a little bit better than what chlorine does. Of course, the staining is a problem. Some people have a little bit of an allergies. It can be a little bit more irritating than some other antiseptics. If we use iodine as a tincture just means that it's dissolved in alcohol. So that's commonly the way we've used it, a tincture of iodine. We found that it's a little bit less irritating if you use it as an iodophore. And an iodophore, that just means that the iodine has been complexed to some kind of carrier molecule, maybe a protein. So that povidone iodine has the trade name of betadine. And that was one of the things that we dipped our discs in lab last week. That's much more commonly used than the tincture of iodine because it's less irritating. So, before needle pokes, this picture is somebody that was having hand surgery, and they washed the whole hand in iodine before the surgery, just to cut down on any possible chance of infection there. So lots of medical applications. Even here's another one, dairy applications. There's something called teat dip, which I kind of laugh at this picture. It's like the cleanest cow I have ever seen in my life. But what they do, they go down, and I have some distant relatives that have a big dairy farm, and I went to see them once, but they kind of hose the cows down a little bit to kind of get, some of the dirt off. And then they'll go down and with this teat dip, go down the row and then allow some contact time, and then come back to the front of the row and wipe that teat dip off, which has iodine in it in some form. Just a way to, again, make the milking process as clean as possible. So they apply it, they do contact time, and then wipe it off again. All right, alcohols are also considered a kind of mid-level, both disinfectant and antiseptic. So ethanol, isopropanol. Isopropyl alcohol is just rubbing alcohol. And by the way, I was reading, here's an application of rubbing alcohol, isopropyl alcohol. If you've got ice on your windshield, which hopefully we won't have too much of today, but you can mix 2 parts rubbing alcohol with 1 part water. And because the isopropanol has such a low freezing temperature, it will melt the ice off of your windshield or whatever. So probably anything that's a de-icer probably has rubbing alcohol in it. Used as an whether it's used as an antiseptic or disinfectant really kind of depends on the concentration. Well, there's not a huge line there. I was noticing in lab, we actually spray 70% ethanol as a disinfectant. Hand sanitizers are somewhere between 60 and 70%. They kind of vary depending on what brand you use. Sometimes I get going down rabbit holes. You read about people drinking hand sanitizer because it's alcohol, right? You don't want to do that. It's a different kind of alcohol. It's denatured alcohol. It will make you sick. And there's additives in there that would make you sick even if the alcohol didn't. So yeah, don't do that. I don't think I needed to say that. But it works primarily by dissolving membranes, kind of intercalates in those membranes, also denatures proteins, so does a lot of damage to cells. Interestingly enough, you do not generally use alcohol as 100% alcohol, because you actually need a little bit of water, a little bit of a dilution is necessary for that surfactant action. So in this case, a little bit of a dilution is beneficial. And besides, 100% alcohol evaporates really, really quickly. And you always need a little bit of contact time. So gotta dilute it a little bit. But it has the advantage of not being irritating to the skin. It's considered an inhalation hazard if you're around a whole bunch of it all the time. But it's very cheap. Somebody asked me last semester, can you use vodka to disinfect a wound? What do you think? Yeah, well, so it depends. I looked this up. It depends on the percentage of alcohol. Vodka is like 40 to 50% alcohol. So, vodka might be a better choice than beer, which is only like 6% alcohol, or wine, which is like 10%. But probably not as good as, just buying some rubbing alcohol or ethanol. It would also be a lot more expensive if you were going to obviously use it on a regular basis. So, so we have to talk about washing hands. Like, we're going to talk about hand sanitizer. Which is better, using hand sanitizer or washing hands? Okay. Let's first define both of them. So if you're going to use hand sanitizer correctly, you're going to use enough so that your hands are wet for 15 seconds. Okay, so however much that amount is, you got to use enough of it. And if you're going to wash your hands correctly, you're going to want to scrub for about 15 to 20 seconds. Okay, that's the number that I read. So we'll go with that. So which is better? Well, here's some drawbacks with hand sanitizer. It's not as effective if your hands are dirty. Again, that's, organic penetration. I went on a mission trip once, we were kind of out in the middle of Guatemala, and before we would eat lunch, we would wash our hands in hand sanitizer, and we thought, oh, we're protecting ourselves. Well, we've been like building stuff, and our hands were probably really dirty, and it's no wonder that a bunch of us got sick. So it's not as effective if your hands are dirty, and things like endospores and naked viruses are not reliably killed. So it's going to do a really good job with influenza, with COVID, and being pretty effective there, again, as long as your hands are reasonably clean. Not so good against things like norovirus, a naked virus. Okay, so for these reasons, it's going to be better to wash your hands. If you have access to soap and water, just that, again, degerming action, you're washing those microbes away and getting them away from your hands, so that, you know, when you rub your face or when you're eating, they're not going to make you sick. So if you don't have access to soap and water, though, yeah, by all means, hand sanitizer is going to do you some good. All right, there's one high-level disinfectant that we'll talk about, and some things I read call this as close to the ideal disinfectant or antiseptic as what we have, and that's hydrogen peroxide. Okay, so H2O2. When it decomposes, it will form hydroxyl radicals. That's one of those toxic forms of oxygen that's going to be, again, pulling electrons away from other molecules and causing all sorts of cellular damage. It's going to denature proteins and break down membranes, just to list a few things. It doesn't leave any residue, so it's really nice that way. It's really inexpensive. One disadvantage, though, is that it is photosensitive. So again, when you buy it, it's in a dark brown bottle for a reason, to try to keep it from being exposed to light. I haven't read like how long it keeps or stays good, but I did read that if you pour a little in the sink and it fizzes, then it's still good. So when it comes in contact with water, it should fizz. Or if you put it on a wound, it should fizz, because we make enzymes that will dissociate that hydrogen peroxide, and you'll see that fizzing action. If it doesn't do that, then it's probably dissociated. That molecule is just a very kind of unstable molecule, and that bond between the two oxygens is kind of something like this. That bond between those two oxygens is just really unstable, and it dissociates pretty easily. We can use this as an antiseptic. Most commonly is a 3% solution. And that's going to be more of a low-level disinfectant or antiseptic. I guess many years ago, like when I was a kid, it was more common to use this as an antiseptic. You know, it wasn't particularly painful to use or anything. It kind of come away from using it as an antiseptic now, because it's fine to use once on a wound, but you don't want to keep applying hydrogen peroxide every day to clean a wound, because that will slow down the healing process, because it's harmful to our cells as well. So yeah, use it once. It's more likely to scar if you keep using it over and over again. So we more often use other things like triple antibiotic cream that work just as well. If we use hydrogen peroxide more concentrated, like 30 to 35%, that's when it's considered sporicidal. Okay, and we could use that either as a liquid or a vapor, even if you were, again, some large space. But it is often used for delicate instruments or cutting instruments. Sometimes when we put cutting surgical instruments in the autoclave and use heat, that kind of dulls them. So sometimes it's better to use some kind of chemical. All right. Questions? Anything that makes you think of? Okay. A lot of people ask me if I'm kind of a germaphobe because I teach about this kind of stuff, and to be honest, I eat stuff off the floor all the time. So not really. There are certain circumstances when you need to be extra careful, like if you're around any kind of fecal contamination. Yes, you wash your hands as hard as you can. You know, raw meat, I'm really careful when I cut up raw meats, especially chicken. But again, most of the time, I don't worry about it too much. Exposure to a wide variety of microbes is good for a healthy immune system. That's my mantra. All right, so we'll just kind of get, this is good introduction to our next chapter here, a little bit lighter material maybe here just to start out. I want to start out our section of antibiotics. Well, it's not lighter. I want to start off thinking about how we die. So I guess I just meant like not so much content that I'm worried about you getting. I just kind of, it's interesting to take a little public health aspect a little bit, you know, before we start talking about our antibiotics. This was the best chart that I could find. I'd like to find a more recent one about the sorts of things that kill us. And this was from the New England Journal of Medicine. So this was in the US. If we were talking worldwide, this would be different. But we're comparing things that kill us in 1900 to things that kill us, you know, recently, 2010. So thinking especially in terms of infectious disease, look at the kinds of things that used to kill us in 1900. Pneumonia, tuberculosis, gastrointestinal infections, things like typhoid, because our water wasn't treated. So basically we're getting fecal contamination to our drinking supply. And then we have heart disease, things like stroke, kidney disease, you know, we still got that stuff, but you know, cancer, when you're talking about the top 10 things that kill us, cancer is pretty low on the list. Here's another infectious disease, diphtheria. We used to have like 40,000 cases of deaths due to diphtheria every year. So now we've almost pushed, again, at least before COVID, we've almost pushed infectious diseases, you know, off the list. Heart disease and cancer are the top two by a long ways. Things like, you know, airway diseases like COPD and emphysema, stroke, accidents, diabetes. Here, number 9, pneumonia or influenza. So we've really done a pretty good job in our fight with infectious disease. If you look at life expectancy, in 1900, life expectancy was, any guesses? 47. That's the number I have. Yeah, that was close. Yeah, that was close. So that doesn't mean that people only lived till they were 46 and they died. It's the average, right? So because so many kids died before their 5th birthday. In 1900, a third of children died before their 5th birthday. So, you know, you had a lot of people that lived till they were 90, but that balances out to like 46. So in 2010, that life expectancy for a white male was 74 years. So we made a lot of progress. What has contributed to that? I'll talk about that in a minute. These were sort of the best numbers I could get from, I looked this up about a year ago, but you know, COVID, whew, yeah, like it's been a huge thing. That was most likely the #1 cause of death in, you know, early 2021. So interesting. I think we're doing better. We're slowing down the deaths there. What kind of things have contributed, again, thinking public health wise, in terms of how are we doing so much better against infectious disease? Well, what they talk about in this chart, just I don't know, just being a little bit organized. Health departments are supposed to educate people about, you know, not just infectious disease, but other things like accidents and how they can stay safe. We started to chlorinate our water. So improvements in hygiene made a huge difference. Look at this spike, that 1918 influenza pandemic. 50 million people worldwide died of that. And again, here, even before we have antibiotics, we have the last person in the US that had bubonic plague. So that was, it was just increasing hygiene. Bubonic plague is carried by the fleas of rats. So again, recognizing we need to keep clean and not keep garbage piled up everywhere helped with that. But then, of course, here's the advent of antibiotics in the early 1940s. That helped. And then we had some vaccines before here. The Salk vaccine, that's the polio vaccine. We started to get really good at making vaccines. Finally got a good measles vaccine. So all those things have contributed. This little uptick that they show there, probably that can be explained by some antibiotic resistance, as well as kind of a backlash at that time of people not vaccinating their kids. It's also about that time, late 80s. That's when they started giving people 3 measles vaccines. They started to recognize, oh, that 5% of people don't get good protection from only 2 vaccines, and that you should have another booster, as a young adult, and then that pretty much protects everyone. So as we move forward here in chapter 13, hopefully this is a chapter that you find interesting. I know that I do. We'll look at a little bit of history and talk some terminology, and then think about, well, what sort of things do we need to think about if you are a doctor prescribing a patient an antibiotic, what sorts of things do we need to think about? Administration and toxicity and allergies and all that stuff. And then we're going to look at a number of drugs. I think it's about 14 or 15 drugs, how they work, where we use them. We'll talk a little bit about drugs that work on other microbes besides bacteria, but just a little bit. I've added that in. We have to talk about resistance a little bit because that's a hot topic now, and how we tested them. If you are in lab, we talked about that today. That was the lab that we missed on Wednesday and Thursday. Okay. I think that's kind of a good, reasonable place to stop. We'll hit the ground running there on Wednesday. I am not having office hours on Friday. Not because I'm leaving to go somewhere warm, unfortunately, but I have an appointment. So I am available now if you want to look at your exam. Wednesday morning I'm available, Thursday, a lot of availability.